goes with secant. Cosine goes with secant. Cosecant over here goes with sine. So a co and a no co. That's how you remember that. Okay? So these are the reciprocal identities. The other identities that we should explore here, we should talk about, I guess, is this tan one. We talked about this, the tangent of an angle, and you can put x in here or theta, right? Very commonly we'll be putting theta in here, is sine over cos. Well, if you can put this together, because tan equals 1 over cotan, then the cotan should equal 1 over tan. Meaning, if we flip this, take the reciprocal of this, and we take the reciprocal of this one as well, then that should be an identity as well, which is absolutely true. Okay? So this is another one we should write down that we're going to be able to use later. Okay, so these are the reciprocal identities that we're going to be exploring here. And they're on page 291 in your textbook. Questions about those? All right, so in this section so far, what you're going to be asked to do is to say, okay, plug in some angles. There's some angle measures. Make sure that this side is the same as the other side. All right, so that's kind of the bulk of what we're going to be doing here. It's pretty easy. All right, let's take a look at at this example 1, and we're going to go through this real quick. We're going to say, and this is what example 1 says: determine the non-permissible values in degrees for this equation. Okay, so this is what example 1 says. A says, what are the non-permissible values? And of course, what we're referring to there are what values for the variable theta will make this statement, will cause one side or both, or the denominator to equal 0, or one side to be undefined, right? We know about non-permissible. So are there any angles of theta that you can see? And I've got a little portion of the unit circle written over here. Any angles for theta that you know are not going to work here? Sorry? 90. Okay, so 90 degrees is over here. Let's see. The cosine is 0. The sine is 1. The tangent is 1 divided by 0. Oh, look at, we've got tan of theta right here. So this is going to be undefined. All right, so that's a good clue that, hey, this might be a problem at 90 degrees here. Okay. What about secant? That's 1 over what? Cosine. Okay. What did we say the cosine was at 90? 0. What's 1 over 0? That's a problem too at 90. Okay. So yes, I like that answer. That theta cannot equal 90 degrees. Anything else that theta really shouldn't be able to, shouldn't equal here as well to make this, any part of this undefined? Anything else there? And yes, I did kind of give you a hint here with these quadrantal coordinates here. Yes, 270. Very good. So we have, there's 90, there's 180. Here is 270. And we have the same sort of situation here, right? Cos is 0. So 270 as well. Bad 270. Okay? So that's a problem as well. And, of course, if we're talking about non-permissible values between 0 and 360, we list those two, and we're good. If it's saying all non-permissible values, so speaking in terms of generality, let's make this a general statement, then what you want to notice is that every multiple of pi past pi over 2, so we got pi over 2, plus or minus pi, right? All of those that end up here and end up here. So that's going to be 90 degrees plus 180, and any multiple of 180, where the n is, of course, in an integer, so plus or minus any multiple of 180. And also, well, 270 plus or minus, 180, okay, or plus 180n. Which, yeah, that's exactly what I want to tell you, is that this, you don't have to do this. You don't have to be redundant with this. It is, some of this overlaps, right? So you don't have to write them both. Now, can I just write 1, or do I have to write something that covers all of this? All right. So yeah, you could just write this one. Okay, you don't have to write this one because it covers everything there. All right, and these are good, right? I guess these ones. Did we look at these ones? Did we look at these ones? Because I'm kind of wondering if those are an issue as well. No one said anything about those. Do we have any problems if it's like 180? Well, I have a problem. The problem is that sine of 180 is 0, isn't that correct? So the secant of 180 is okay. The tan of 180 is okay. But the sine of 180, we're going to be dividing by 0 there. Is that right? Does that actually make sense? Okay. All right, so we do have to, this is great, but we're not done because we have to also look at this one. And you know what's the same over here too, right? So theta can also not equal 180 or 360 and so on. So now what we have is we have 0 degrees plus 180n. Or we have every multiple of 90 degrees. So the actual final answer here is 90 degrees plus, you could say 90 degrees plus every multiple of 90, or you could do 0 plus any multiple of 90, which in simplest terms, I don't want to get you too confused here, but this right here actually would be the simplest way to write this, 0 plus 90n. Okay, so this is okay if that's kind of what you see, like, oh, every multiple of 90, I'm going to do that. 90 degrees is the first one, then every multiple of 90. But you can also just realize that, hey, these are the non-permissible values for theta. So theta cannot equal any multiple of 90 degrees. So to continue this example, it just says test out, theta of 60. Test out what this would look like at 60, which we kind of did that. I'll do that real quick with you. At 60 degrees, the secant, which is 1 over cosine, is what? What is it? Right here, 2. Okay, at 60 degrees, it's 2, because these are the coordinates on the unit circle. So cosine is 1/2. 1 over cosine is 2. Tangent, okay, what's the tangent? Well, that's when we do sine divided by cos, so root 3 over 2 divided by 1 over 2, which is the same as root 3 over 2 times 2 over 1, which is actually the same as just root 3. So this is root 3, and sine is root 3 over 2. All right, so does this simplify to be, the same? Well, if we divide by a fraction, that's the same as multiplying by the reciprocal. And of course, the root 3's should cancel out, and you have yes, 2 equals 2. So that works out if you take that test point as well. Okay, so in your assignment, when it says do a trial at 60 degrees or whatever, then from your unit circle or even from your calculator, right? If it's like random, like 73 degrees, you can just pump the values in your calculator, no problem. But show your steps, I guess, so we can see that they're the same. Because this is the thing, okay? In this chapter, when we're talking about proof, this is when showing your work becomes super important, okay? Because what I'm going to say coming up is like prove that this equals this. And if you just give me, what the calculator says this is and what the calculator says this is for one given angle, and that's your proof, that's not going to cut it, okay? Showing your steps in kind of changing what the one thing looks like so that it looks like the other thing, That's what's going to be important. So make sure you show your work. And finally, in the example, it says to graph. So I'm just going to do that. You don't have to grab a calculator here. I'll just show you up here. But if we graph this, so remember, if I turn this into a graph, say I'm going to graph y equals secant and y equals tan over sine, okay? Then if they're the same for all values of x, what should the graphs look like? What would be the relationship between those two graphs? They should be what? They should be the same, okay? Now I started this already on this calculator, so secant. Notice that there is no secant button. No secant. And secant is not sine to the negative 1 or cos to the negative 1 or tan. Those are not, secant isn't up here. It's not cos to the negative 1. It's actually 1 divided by cos, okay? So that's super important when you're graphing this. Make sure it's 1 divided by cos, because that's the function that you have in your calculator. If you go down to the next line here, we could do tan of x, a bracket, divided by sine of x. Okay, so bracket around that. And then you can graph those two. This is what the first one, okay, all right. Problem. You know what the problem is? Anybody know? I put it into degrees, yes, before for the other one. So I need to put this back to radians. You can still graph it with degrees, but you just have to make your x-axis now, instead of being like, 0 to 6 or something, you have to put like 0 to like 720. So anyways, so if we graph that, there we go. Yeah, that's what 1 over cos looks like. And we'll talk about graphing reciprocal functions later too. Doesn't that look great? You guys look like you're just being tortured looking at that. It's beautiful. That's what it is. Beautiful. It reminds me of like some sort of European, like, church or something. Or a bridge or a castle. Yeah. See, isn't that great? Oh, wow. Now you like it. Okay. Oh, so here, guys, watch this. Watch this. I actually I graphed both of these, right? And they only showed up as one graph. That's actually one graph. Okay? So they're the same. Now, if I did something like, let's say I did something like this, plus 2 onto this one. If they are the same, now that I do this plus 2, what should that do to this whole graph? It should move it, yeah, that's right. It should move it up. So let's see if that actually happens. I might need to put some brackets in here, but I think that should be good. So here's our first one. There's the first one. Okay, the castle. Oh, there's the other one. Look at that. So it is shifted up. Now it really looks like a bridge. True. So it looks like, to me, it looks like a series of happy faces and then sad ones. Yeah, mustaches maybe. Very good. Okay, guys are creative. Awesome. So you see how they're the same? So I take that 2 off there now, pull it back down, and then, yeah, it's the same. So graphing, if you graph the two functions and they actually map exactly onto each other, that means that for every x value, they're going to produce the exact same y value because they're like the same graph. Okay, need to keep going. One more set of identities I need to talk to you about, and that is the Pythagorean identities. These are going to become very important in the future, but what I want to show you is this. Pythagoras' theorem. Okay. If we start with a right triangle and we have a right triangle like this, we know that Pythagoras' theorem is a squared plus b squared equals what? C squared. Yeah. And now we've been working with this for years, and we know that for every right triangle, this relationship holds true. This is an identity. Okay? Pythagoras' theorem, that's an identity. Okay? The sum of the squares of the legs of a right triangle equal the square of the hypotenuse. We know that to be true. Now, if we transfer this from just some random right triangle, and what if I wrote this? That this x value here is actually cos of x, and this here, because we're on a unit circle, this is actually sine of x, and on a unit circle again, this is 1.